Hello everyone, welcome back. Why does a capacitor allow current at one time and completely stop it after some time? Why does its voltage never change instantly? Why does it behave like an open circuit in DC but almost like a short circuit at a very high frequency? The answer is hidden in how a capacitor stores energy. What is a capacitor? A capacitor is a passive two-terminal electrical element that stores energy in the electric field created by separated charges. The simplest capacitor consists of two conducting metal plates and insulating material between them called a dielectric. The plates do not touch. A capacitor stores energy by creating charge separation. What is inside a metal? A metal contains fixed positive metal ion cores and free electrons. Normally, positive charges equal to negative charges, hence net charge equal to 0. The metal is electrically neutral. Connect a battery here. Positive terminal of the battery connected to plate A, negative terminal connected to plate B. The battery creates an electric field that moves electrons. How does a capacitor charge? Consider the positive plate. The positive terminal pulls electrons away, causing the electrons to leave. The plate loses electrons. The positive metal ions remain. The plate gets a net positive charge. It is not because positive charge was added, it is because electrons were removed. Now consider the negative plate. The negative terminal pushes electrons onto the plate. Extra electrons accumulate. The plate becomes negatively charged. Why don't charges cancel? The negative plate electrons are attracted towards the positive plate. They want to move, but the gap contains a dielectric. A dielectric is an insulator. It does not allow free electron movement like a metal. So charge separation remains. What does the dielectric do? The dielectric contains atoms, normally like this, that is, charges balance. When an electric field exists, the charges inside the atoms shift slightly. The molecule becomes a dipole. Millions of molecules align. This is called polarization. Why does dielectric increase capacitance? The capacitor creates an electric field. The polarized dielectric creates an opposing field. The total electric field decreases since voltage depends on electric field. As electric field decreases, voltage decreases. If the battery is still connected, the battery pushes more charges onto the plate. Therefore, charge increases. C equal to Q by V. More charge for the same voltage means higher capacitance. Where is energy stored? The battery does work to separate charges. It removes electrons from one plate, adds electron to the other plate. That energy is stored in the electric field. Capacitance. Capacitance tells how much charge is stored per unit voltage. General definition is given as C equal to dq by dV. For a linear capacitor, C equal to Q by V. And the unit is farad. Higher capacitance means more charge stored for the same voltage. Parallel plate capacitor, that is, for a parallel plate capacitor, C is given as epsilon A by D, where A is plate area, D is distance between plates, epsilon is permittivity. If area increases, capacitance increases. If distance between plate decreases, capacitance increases. Discharging a capacitor. Now remove the battery. The charges remain separated. So when you connect a resistor, the resistor creates an external path. Electrons do not cross the dielectric, they move through the resistor. The stored field energy becomes heat. Capacitor current voltage relation. Current is nothing but rate of charge flow, that is dq by dt. Since q equal to Cv, we get I equal to C into dV by dt. Current depends on how quickly voltage changes. Capacitor switching rule. The capacitor voltage cannot change instantly. That is, voltage at 0 minus is equal to voltage at 0 plus. And that's because a capacitor stores energy through charge separation. The relation is Q equal to Cv. To change voltage suddenly, charge must change suddenly, but I equal to dq by dt. A sudden voltage change means dV by dt tends to infinity. Therefore, I, which is C into dV by dt, also tends to infinity. An infinite current pulse would be required. In real circuits, this cannot happen. Therefore, capacitor voltage is continuous. Before switching, if capacitor voltage is 5 volt, immediately after switching, capacitor voltage is still 5 volt. The capacitor remembers its previous voltage, but current can change instantly. Next is DC steady state. Initially, current flows because the capacitor is charging. After a long time, voltage becomes constant. Therefore, dV by dt is 0, hence I is 0. An ideal capacitor becomes open circuit. Now let's consider capacitor in AC circuits. Capacitive reactance is the opposition offered by a capacitor to AC current, that is Xc. Capacitive reactance is given as 1 by omega c, which is nothing but 1 by 2 pi Fc. Here Xc is capacitive reactance, F is frequency of AC supply expressed in Hertz, omega is angular frequency, C is capacitance in farad. As frequency increases, capacitive reactance decreases. At very high frequency, Xc tends to 0. The capacitor behaves like a short circuit. Capacitive impedance. Capacitive impedance is the total opposition offered by a capacitor to AC current, including the magnitude, how much it opposes current, and phase information, that is how voltage and current are shifted. Capacitive impedance Zc is given as 1 by j omega c, that is minus j into 1 by omega c. The negative imaginary part here means current leads voltage by 90 degree. Energy stored is given by the equation half into Cv square, and the energy is stored in the electric field. RC transient response. RC transient response is the time-dependent behavior of voltage and current in a circuit containing a resistor and a capacitor when the circuit is subjected to a DC excitation like step voltage, or when initial energy stored in the capacitor is released. The speed of the transient response is decided by the time constant tau given as R into C. Charging. V of t is V into 1 minus e to the power minus t by tau. At t equal to tau, voltage reaches 63.2% of final value. During discharging, V of t is V naught e to the power minus t by tau. Let's consider the series and parallel equations for a capacitor. In case of parallel connection, since voltage is same, charge adds up. Equivalent capacitance is given as C1 plus C2 plus C3 and so on. In case of capacitors connected in series, charge is same, voltage adds up, and equivalent capacitance is given as 1 by C equivalent equal to 1 by C1 plus 1 by C2 and so on. Finally, what we need to understand is inductor stores energy in magnetic field, current cannot jump there. But in capacitor, since it stores energy in electric field, voltage cannot jump.